The purpose of this tutorial is to show you how to select and view a variety of simulation outputs so you can analyze the data and assess the predicted building performance. During this tutorial, I'll show you how to select data for analysis from display options and the info panel. I'll introduce the different display formats such as graphs and grids. And finally, I'll show you how to quickly and easily generate temperature distribution graphs, which can be used to produce summer overheating reports. Data can only be viewed if it was selected as a simulation output in the calculation dialog, as described in the earlier tutorial on setting up simulations. The zone must also be switched on in the Activity tab via the Include Zone in Thermal Calculations option, if it's to be included in the simulation. All zones in this model are switched on, as you can see here in the navigation panel. None are greyed out. Here is the dialog showing the output options are selected to generate the simulation results that I'll review during the tutorial. It's a summer design week simulation with daily, hourly and sub-hourly reporting intervals set to 2 time steps per hour. The graphable outputs I've selected are surface heat transfer including solar. Note that this is required to display fabric data in the results. Environmental for temperatures and humidity, etc. Comfort, internal gains, energy and HVAC, and fresh air supply. I'll show you how to generate a quick temperature distribution simulation later in the tutorial. Note that I've only requested data during occupied periods, and I've also selected the Annual Building Utility Performance Summary, or ABUPS, report. Any selected reports will be shown in the Simulation Summary tab on completion of the simulation. The initial view after running a simulation is dictated by the display options, which will either be set to default when first simulating a model or will reflect the settings used for the previous simulation. If the options under the data header are set to display data which was not generated by the simulation, such as monthly data in this case, you'll see this screen. The Update Data screen prompts to see if you wish to update the simulation to generate the results requested under the data header. If you did request all required outputs in the Calculation Options dialog, that data will be stored, and you can simply change the Data Display option to view the results. I'll select the daily interval, as that was one of the intervals selected in the Calculation Options dialog. The subject or title of each individual graph is shown on the left here with relevant units, and the time and date to which the graphical information relates is displayed along the x-axis. The daily time interval can be used in the graphical format to provide information on trends over longer simulation periods, but as you can see, it's not much use when looking at design week information. I'll change the interval to sub-hourly and also increase the text size to medium to improve readability for the more detailed information. You can select the data you wish to view either from the display options here or from the info panel here. Before doing anything, you should check that you're at the correct level in your model. I'll stay at building level to look at some of the options available there. Moving on to the data header options, we can select the data group to display from this drop-down box. The All option displays key information depending on the building level selected. So here at building level, we can see information such as fuel consumption, temperatures, and internal gains. Note that at building level, data such as internal gains and temperatures are floor area weighted averages for the building. Data like this is clearly more meaningful at zone level. Site data graphs the key hourly weather data outputs and displays information like wind speed and direction, which can be very useful when interpreting natural ventilation calculation results. Comfort shows the air, radiant and operative temperatures and outdoor dry bulb temperature and relative humidity levels as standard. These additional comfort metrics, such as Fanga PMV, are shown if the comfort output option is selected. You'll notice that data for unoccupied periods is not shown, as this data was omitted from the output options. Internal gains shows the graphs of gains from equipment, lighting, occupancy, solar and HVAC heating and cooling delivery. As this is a heat balance graph, negative values shown below the 0 point on the y-axis indicate heat loss from the space. Fabric and ventilation shows the heat gains to the space from the surface elements, walls, floors, ceilings, etc., and also ventilation. The following options are only available at building level. The fuel breakdown, which shows the fuel consumption broken down by system category, such as lighting and chiller electricity. Fuel totals shows the total consumption for each fuel type. As you'd expect for a summer design week simulation in a building with electrically heated domestic hot water, there is very little gas consumption. CO2 production gives the mass of CO2 produced. This is calculated based on the CO2 emissions factors set up for the region at site level. System loads shows the heating and cooling loads, i.e. the heating and cooling energy delivered by the HVAC system. This excludes other zone energy inputs, such as internal gains, which are shown on heat balance graphs. I'll show you how to generate custom data later in the tutorial. The selected summary reports, such as ABUPs, are shown here in the Summary tab. Scrolling through the ABUPs report, you can see it contains key statistics and a useful breakdown of fuel energy consumption broken down in various ways into end-use categories. At zone level, you can see that the building level options such as fuel and CO2 are not available. We can also select the data to view from the Display Shortcuts section here in the Info panel. I'll start by clearing all the data, and then I can add whatever data set I'm particularly interested in. One of the most useful displays is the one showing the heat balance from internal gains. and viewing it in isolation provides better visibility as it's displayed over the full area of the screen. This type of data is generally more meaningful at zone level, where we can get a very good feel for the heat loads being generated in the zone. You can see that the general trend of higher solar gain in the morning, as you would expect in an eastern zone in the northern hemisphere. Although this zone does also have north and south facing glazing. This will also clearly depend on the weather data, which may include higher solar gain values in the afternoon. We can see that this is the case on at least 2 days by looking at the site weather data. When analysing performance in detail, it's often useful to look at the more involved graphs, such as those showing the internal gains over shorter time periods. I'll enter the time period of 1 day in the days per page and apply this using the tick icon. Note that pressing the Enter key on your keyboard has the same effect. Scrolling through the simulated days, the first 2 days show only site weather data as there's no occupancy over the weekend. Looking at Monday's data, we can see that the 2 dominant gains are solar gains from external glazing, which peaks in the morning, as would be expected in this zone, and lighting. This immediately shows us the areas we could consider targeting to reduce internal gains by fitting some form of window or external shading device and either reducing lighting loads and possibly also introducing daylighting controls on luminaires. Lighting improvements have the dual advantage of reducing both lighting energy consumption and reducing uncontrolled heat gains into occupied zones during the cooling season. The other significant gains are due to the equipment and occupancy. You could review and possibly alter these in the Activity tab if you're sure they don't represent your own design criteria. However, note that these values may have been taken from the schedules based on the national standards, so beware of changing them when undertaking Energy Code compliance simulation. The final internal gain shown is that due to internal glazing. The solar distribution option in the calculation options was not set to full interior and exterior for this simulation, so this data will only cover diffuse radiation. For more accurate analysis of solar gains through interior windows, you must use the full interior and exterior solar distribution option. As this is a heat balance graph, it also shows the zone sensible cooling load below the 0 kilowatt line on the graph. The cooling load is used to ensure that the cooling set point temperature for the zone is met for each time step where the cooling system is operating. In most cases this will balance, but you must bear in mind that the heat balance graph will only give an approximate balance for various reasons that are explained in the program help. You can see the effect that ambient air has on the cooling load if I also select the heat balance option. Which shows the additional infiltration and ventilation heat gains and losses in the top graph. You'll also note the beneficial effect that infiltration has in removing heat gains outside occupied hours during this peak summer period, It's generally better to achieve this through a controlled night ventilation strategy rather than uncontrolled infiltration, which would have an adverse effect during cold winter conditions. I'll clear this data and select the comfort option, which shows the zone temperatures throughout the day at the top. On Monday you can see that the ambient dry bulb air temperature peaks at around 30 degrees C during mid to late afternoon. The graph shows that air temperature is being controlled to the cooling set point of 24 degrees C. And you may remember that the air temperature was set as the controlled parameter in our calculation options. The radiant and resulting operative temperatures are not directly controlled, and you can see that the operative or comfort temperature peaks during the early afternoon. The comfort metrics such as Fanga PMV are shown below the temperature and humidity graphs when the comfort option is selected as a simulation output. There are no reported discomfort hours. However, the Kansas University thermal sensation vote in the bottom graph indicates a reduction in comfort during the early afternoon. Up to now, I've only used the main data display options. These can be tailored to meet your own needs using the options in the Detailed tab. Here, for example, I may wish to view the gains data for Monday without the zone sensible cooling. So I can deselect that option from the list and apply it using the tick icon, and going back to Monday you can see that the zone sensible cooling has been removed. I'll add it back in. I can also add any data to the view providing it was generated during the simulation. For example, I may wish to assess the correlation between ambient and comfort temperatures. I simply add the comfort temperature from the environmental options and the dry bulb temperature from the site weather options and use the tick to apply the data. Increasing the days per page to 5, I can scroll across to get a picture of the relationship between these interconnected variables. You can change the size of each graph by left-clicking the border and dragging to the required height. Here I'll expand the size of the more detailed lower graph to get a better overall picture. If I have a particular data set or sets that are used regularly, I can save them as templates. Here I'll save this display option as the tutorial template. You can then select that display option at a later date from the custom data option here. Designbuilder provides the option of displaying the results in different formats, which can either be used directly or exported for further analysis, or to use as data within reports. Exporting results and using the data to compile reports is covered in a later tutorial. All of the data reviewed so far has been in this graph format. Selecting option 3 from the Show As drop-down box enables us to add a table to the graph, so we can instantly see each value at a range of time steps. This can be really useful when showing information like temperature distribution graphs in reports. Note that when a lot of data is displayed, there's not room on the graph to display all data in table form, so only data at selected times is shown. Option 2 shows the information in grid form with all data tabulated, and this option must be selected to export data to a spreadsheet. It can still be a useful tool to use within Designbuilder. For example, selecting the comfort data and then by clicking on a column header we can sort the data from the highest to the lowest value. We can, for example, then quickly identify our peak operative temperature during the occupied periods over the simulated time period, which is 27.18 degrees C. Option 4 shows the summary table that we saw in option 2 but without the graphical data. Selecting the Normalize option displays relevant information per unit of floor area. As we have metric units specified in program options, the relevant data units will be displayed per metre squared, such as the heat balance value shown here. The Y-axis options give you control over how the Y-axis is displayed. You can lock the extent of the Y-axis so that it keeps its current maximum and minimum values. This ensures consistent comparison with any future results displayed. The axis can be locked either by selecting and applying with a tick, or using the toolbar icon here. With this option selected, the Y-axis keeps its current setting until you unlock it again. You can manually change these individual settings by altering the text value and applying with the tick icon. The Overlap Multiple Axes option allows you to save space on the Y-axis, allowing different axes to overlap. Like here, for example. The Separate Axes option is selected by default to add a vertical space between each of the displayed axes, but can be unchecked if desired. You can change the display font size here under the appearance header. As shown earlier, setting this to medium often helps provide more informative graphs on smaller screens. You may wish to try the other options under the appearance header to see how they affect the appearance of the results screen. Temperature distribution was not selected as a graphable output prior to running this summer design week simulation, as this data is generally used to produce seasonal or annual results. Selecting the temperature distribution calculation output option enables you to graph how many hours per year each zone is at, above and below each temperature band. This information is only generally useful for zones which are normally occupied, so you may be able to switch off unoccupied zones such as stores and WCs after giving due consideration to the impact on the occupied zones which are included in the simulation. If temperature distribution is the main purpose of your analysis, for example to produce a summer overheating report showing hours over 28 degrees C in occupied zones, you can deselect the other calculation output options and request only temperature distribution and monthly and annual data, enabling you to produce these results very quickly. Temperature distribution data is only normally meaningful at zone level, so we can deselect the building and block output option. The results are often presented as the number of hours above a threshold temperature as a percentage of the total number of occupied hours, so I'll set the simulation to report only occupied periods. The annual simulation with those output options took less than 3 minutes to run on my computer, although you should bear in mind that calculated natural ventilation simulations will take much longer. I now need to change the display data option to comfort to view the distribution graph. I'll also select the graph and table option, which is particularly useful for analysing and reporting on temperature distribution. Before reviewing the results, you should check that the radiant fraction is set correctly. This is normally the operative temperature, but can be air temperature depending on the particular standard the building design is being compared against. Starting from the top, each graph clearly shows the zone for which the results apply. It shows that the hours are recorded for the whole year, but only for occupied periods, which are determined by the occupancy setting in the Activity tab. The three graphs and the useful table below show how many hours each zone is below, at, or above each 1 degree C band or bin of the selected temperature radiant fraction metric, which I just confirmed is the operative temperature. Each temperature bin represents the number of hours spent in the temperature band 0.5 degrees C either side of the stated number. The total number of occupied hours is the higher figure shown at each end of the temperature scale on the x-axis. In this case, 3,132 hours. The range of temperatures shown on the x-axis is the full range of zone temperatures experienced during occupancy. So this graph shows that the operative temperature in the ground floor east zone never went below 17.5 degrees C or above 27.5 degrees C during occupancy. We can view the graph for each zone in the building via the navigation panel in the normal way. This tutorial has provided all the information you need to select and analyse simulation results in Designbuilder. I've hopefully demonstrated how easily you can generate data which can help you optimise your building design and help you meet regulatory and energy code requirements. I'll show you how to export this data in a variety of formats in a separate tutorial.